On a clear night, the Milky Way looks peaceful, a soft river of light stretching quietly across the sky. But 26,000 light-years from where you are standing, something is deeply wrong. At the exact center of our galaxy, scientists keep finding things that do not fit. Stars racing at 8% the speed of light around a black hole 4 million times heavier than the Sun, a surplus of gamma rays that no one can fully explain. Nearly 1,000 magnetic threads standing upright, like the strings of a ghostly harp with no player. Pulsars that should exist by the hundreds, but have almost entirely vanished. Giant bubbles of radiation erupting tens of thousands of light-years above and below the core. None of these anomalies exist in isolation. They are all stacking on top of each other in the same place. If you enjoy deep dives into the real mysteries that keep astrophysicists up at night, a like and a subscribe genuinely help this channel keep going and bring more stories like this one to your screen. Now, settle in. Get yourself comfortable. Let's begin. Go outside tonight. Find a dark stretch of sky away from streetlights and let your eyes adjust for 15 minutes. Eventually, a pale band of light will appear. It stretches from horizon to horizon. Soft, quiet, unhurried. That glow is the combined light of hundreds of billions of stars packed into the disk of our galaxy, and it looks like the most peaceful thing you have ever seen. It is a lie. That glow hides the most violent region in the entire Milky Way. Right behind it, buried under 26,000 light-years of gas, dust, and intervening stars, sits a place where gravity bends the paths of light itself, where stars whip around invisible anchors at thousands of kilometers per second, where objects that should have been torn apart long ago continue to survive in orbit so tight they would fit inside our own solar system. And every decade, every new instrument pointed at this region, every new wavelength of light used to peer through the murk, reveals another thing that does not fit the models. Not a small discrepancy, not a rounding error, a genuine and growing stack of anomalies piling up in the same cosmic location. This is the story of what scientists are finding at the center of our galaxy. Not one discovery, not one headline. A whole environment of overlapping mysteries clustering in a region smaller than the distance between our Sun and the nearest neighboring star. And to understand why this is causing quiet alarm across multiple branches of astrophysics, we need to start at the anchor. The thing holding it all together. The thing making everything else in this region so extreme. Sagittarius A star. The supermassive black hole at the center of the Milky Way weighs approximately 4 million times the mass of our Sun. That number sounds enormous, and it is. But among supermassive black holes, it is actually modest. The black hole at the center of the galaxy, M87, the first one ever directly imaged, weighs 6.5 billion solar masses. Sagittarius A star is more than 1,500 times lighter. But what makes our central black hole so important is not its mass alone, it is its proximity. At roughly 26,000 light-years from Earth, Sagittarius A star is the nearest supermassive black hole to us by an overwhelming margin. That closeness gives astronomers the ability to study its environment in a level of detail impossible for any other galactic nucleus in the universe. And the details are strange. Sagittarius A star sits inside a region that astronomers call the central parsec, a sphere of space roughly 3.25 light-years across, centered on the black hole. By cosmic standards, this is a tiny volume. But what happens inside that tiny volume violates expectations in ways that have kept researchers arguing for decades. Start with the stars. The central parsec is crowded. Stellar densities here are millions of times higher than what we experience in our solar neighborhood. Stars are packed so close together that if you were standing on a hypothetical planet in the central parsec, your night sky would blaze with thousands of stars bright enough to cast shadows. In our neighborhood, the nearest star to the Sun is just over 4 light-years away. In the galactic center, you could fit dozens of stellar neighbors within that same distance. The gravitational environment is chaotic, dynamic, and utterly unlike the calm suburban orbit our solar system traces through the galaxy's outer disk. Within this crowded stellar downtown sits the S-cluster. This is a group of stars orbiting so close to Sagittarius A star that their motions have been tracked individually for more than 2 decades by teams using some of the most powerful telescopes on Earth. The star S2 is the most famous member. It completes one full orbit around the black hole every 16 years, swinging as close as roughly 120 astronomical units at its nearest approach. For context, 1 astronomical unit is the distance from Earth to the Sun. Neptune orbits at about 30 astronomical units. Pluto averages around 40. S2 dips within 3 times Neptune's distance from the Sun, but instead of orbiting a quiet star, it orbits a 4 million solar mass black hole. At closest approach, S2 reaches speeds of roughly 7,700 kilometers per second. That is approximately 2.5% the speed of light. A star, a massive luminous ball of nuclear fusion, moving fast enough that relativistic effects become measurable. And S2 is not even the fastest. S4714 holds the current record for the closest known approach to Sagittarius A star. At periaps, the point of closest approach, S4714 swings within approximately 12.5 astronomical units of the black hole. That is closer than Saturn orbits our Sun. At that distance, S4714 reaches speeds estimated at around 8% the speed of light, roughly 24,000 kilometers per second. Those figures carry large uncertainties because measuring stellar positions at these extreme distances and speeds pushes instruments to their limits. But even the conservative estimates place S4714 in a regime where general relativity is not a subtle correction. It is a dominant factor shaping the orbit. The tracking of these orbits earned Andrei Arges and Reinhard Genzel the 2020 Nobel Prize in Physics, shared with Roger Penrose. Their decades of observations confirmed beyond reasonable doubt that the compact mass at the center of the Milky Way is indeed a supermassive black hole. The orbital data are so precise that they have been used to detect the Schwarzschild precession of S2, a relativistic effect predicted by Einstein's general relativity in which the orientation of an elliptical orbit slowly rotates over time. The measured precession matched the prediction almost exactly. General relativity passed another test. But here is where the trouble starts. The S-cluster stars are young. Spectroscopic analysis shows that many of them are massive, hot, blue stars with lifetimes measured in millions of years, not billions. These are not ancient stellar survivors. They are young, energetic objects, and they have no business being where they are. The problem is called the paradox of youth, and it is one of the oldest unresolved headaches in galactic center science. Massive stars form from collapsing clouds of molecular gas. That process requires relatively calm conditions where gas can cool, fragment, and collapse under its own gravity. The central parsec around Sagittarius A star is the opposite of calm. Tidal forces from the black hole are enormous. Any standard molecular cloud drifting into this region would be shredded by those forces long before it could collapse into stars. The gravitational tides rip apart structures that are not dense enough or compact enough to resist. So how did these young stars get there? 2 main hypotheses exist. The first is that they formed farther from the black hole, in a more hospitable environment, and migrated inward over time through dynamical processes like the inspiral of a dense star cluster. The second is that they formed in place from an unusually dense accretion disk of gas that once surrounded the black hole, a disk massive and dense enough to resist tidal disruption and fragment into stars despite the extreme conditions. Neither explanation is fully satisfying. Cluster and spiral models struggle to deliver stars into orbits as tight and eccentric as those observed. Disk fragmentation models require specific conditions that may be physically plausible but have not been confirmed. The paradox remains open. Young, massive stars orbit the black hole in defiance of standard formation models, and nobody has a clean answer. But the S-cluster is only one part of the gravitational puzzle. The dusty objects orbiting Sagittarius A star add another layer of confusion. These are the G objects, first identified as G1 and G2. When G2 was discovered and its orbit calculated, astronomers predicted that it would pass dangerously close to the black hole around 2014 and possibly be torn apart by tidal forces. The encounter was watched with enormous anticipation. Some researchers expected to see the object stretched and shredded, with material feeding into the black hole and producing a dramatic increase in accretion activity. It did not happen. G2 survived. It passed through periapse, got stretched along its orbit, but remained largely intact. This suggested that G2 was not simply a diffuse gas cloud, as some models proposed, but something more resilient. One leading interpretation is that G2 is actually a binary star merger product. Two stars that collided and produced an inflated dusty envelope around a dense core. The dense core would be massive enough to hold itself together against tidal forces, while the surrounding dusty shell gets distorted but not destroyed. A study published in late 2025 by a team led by Florian Peisker at the University of Cologne used the EH-RIS instrument at the VLT to confirm that several of these dusty objects, including G2, maintain stable orbits around the black hole. They are not being swallowed. They are not being torn apart. They are surviving in a region where survival itself needs explaining. Even more striking was the 2024 discovery of D9, a binary star system within the S cluster. This was the first confirmed binary star detected in the immediate vicinity of a supermassive black hole. Binary systems are fragile. The gravitational influence of the black hole should separate loosely bound pairs over relatively short timescales. Finding an intact binary this close to Sagittarius A star suggests either that the binary is very young and has not yet been disrupted, or that the conditions in the S cluster allow for binary survival in ways that current models do not fully predict. The researchers noted that if binary stars can persist in this environment, it may be plausible that even planets could exist in orbit around stars near the galactic center. That possibility has not been confirmed, but the fact that it was raised at all illustrates how much the central parsec keeps defying expectations about what can and cannot survive near a supermassive black hole. Then came the images. In May of 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star. The image showed a bright ring of emission surrounding a dark central shadow, consistent with theoretical predictions for the appearance of a black hole's event horizon, silhouetted against superheated gas. The ring measured roughly 50 microarc seconds in diameter, matching expectations for a 4 million solar mass black hole at a distance of 26,000 light-years. The image was a triumph. It confirmed the shadow predicted by general relativity and provided direct visual evidence that Sagittarius A star is indeed a black hole, not some exotic alternative compact object. But the image also revealed problems. Sagittarius A star is a difficult target. Unlike the supermassive black hole in M87, which is over 1,500 times more massive and changes its appearance on timescales of days to weeks, Sagittarius A star is small and fast. The gas orbiting close to its event horizon completes a full revolution in just minutes. This means the source changes significantly even during a single night of observation, blurring the data and making it enormously difficult to reconstruct a stable image. The EHT team had to develop new algorithms to account for this variability, averaging over rapid fluctuations to extract the underlying ring structure. The resulting image clusters into several possible morphologies, and while the dominant interpretation is a bright ring with an asymmetric brightness distribution, the rapid variability of the source introduces uncertainties that do not exist for M87. Then, in March of 2024, the collaboration released something even more provocative. They published the first image of Sagittarius A star in polarized light. Polarization reveals the structure of magnetic fields near the black hole, and the result was startling. The magnetic field configuration around Sagittarius A star looked remarkably similar to the one around the black hole in M87. Both showed strong, organized magnetic fields spiraling around the event horizon shadow. This similarity was unexpected because the two black holes differ enormously in mass, accretion rate, and environment. M87's black hole produces a powerful relativistic jet, visible across millions of light-years. Sagittarius A star does not appear to have such a jet, or at least, no jet has been directly confirmed, but the polarized light data hinted at something. The magnetic field structure observed around Sagittarius A star is consistent with what physicists call a magnetically arrested disk, a state in which magnetic fields become so strong that they partially obstruct the inflow of gas onto the black hole. In M87, This magnetic configuration is associated with jet launching. The similarity raised the possibility that Sagittarius A star may harbour a hidden jet, one that is either too faint, too compact, or pointed in the wrong direction for current instruments to detect easily. If such a jet exists, it would change the energy budget of the galactic center significantly and could help explain other phenomena observed in the region. This is the gravitational layer of the galactic center anomaly stack. Before we even begin to look at radiation, particles, or signals, the gravity and stellar dynamics alone are already generating unresolved tensions across multiple fronts. Stars orbit at relativistic speeds in configurations that challenge formation models. Objects survive where disruption was expected. A binary star system persists where tidal forces should have separated it. The first images of the black hole confirm general relativity's predictions, but simultaneously reveal magnetic structures that suggest hidden activity, and the mass enclosed within the innermost orbits, constrained by the measured precession of S2, implies that the stellar environment around the black hole may have been significantly depleted by high-velocity destructive collisions between stars over cosmic time, adding yet another modelling challenge. A 2025 study accepted by astronomy and astrophysics examined how a granular distribution of stellar mass objects orbiting within the S2 orbit could produce detectable deviations in S2's trajectory. The researchers found that during S2's next apocenter passage in 2026, gravitational perturbations from nearby objects could exceed the measurement precision of the gravity instrument, potentially allowing astronomers to directly detect the influence of the hidden stellar population around the black hole. If confirmed, this would open a new observational window into the mass distribution of the central parsec, turning the S-cluster into a gravitational laboratory unlike anything else in the galaxy. Every one of these observations, the paradox of youth, the survival of G objects, the binary system D9, the EHT images, the polarized magnetic fields, the hidden jet hypothesis, the constraints from orbital precession, points to the same conclusion. The gravitational environment around Sagittarius A star is more complex, more dynamic, and more difficult to model cleanly than any simple picture of a quiet black hole sitting at the center of a galaxy would suggest. And gravity is only the first layer. What comes next involves radiation that should not be there, an excess of gamma rays that has been argued about for over 15 years, and a missing population of dead stars that, if they truly have vanished, might be telling us something unsettling about the invisible matter concentrated at the very heart of the Milky Way. The gravitational anomalies of the galactic center are strange enough. The radiation anomalies are about to make them look simple. The gravitational weirdness of the galactic center is visible, at least in principle. Stars can be tracked, orbits can be plotted, masses can be calculated, but the next layer of anomaly at the center of our galaxy is not something you can watch move across a telescope's field of view. It is an invisible excess, a surplus of energy arriving from the direction of the galactic core that no confirmed source can fully account for, and it has been confounding physicists for more than 15 years. To understand why this surplus matters, you first need to understand how gamma-ray astronomy works. Gamma rays are the most energetic form of light in the electromagnetic spectrum. A single gamma-ray photon carries millions to billions of times more energy than a photon of visible light. These photons are not produced by ordinary warm objects like stars and gas clouds. They are produced by extreme processes, particles accelerated to nearly the speed of light slamming into other particles, matter falling into black holes, the intense magnetic environments around neutron stars, the violent shock waves from supernova explosions. Gamma rays are the fingerprints of the universe's most extreme physics. But gamma rays cannot be detected from the ground. Earth's atmosphere absorbs them. To study the gamma-ray sky, you need a telescope in space. The Fermi Gamma-Ray Space Telescope, launched in 2008, carries an instrument called the Large Area Telescope that maps the entire gamma-ray sky every 3 hours. Over its years of operation, Fermi has built the most detailed picture of high-energy emission across the Milky Way and beyond. And one of its most persistent findings is a signal that nobody expected and nobody has been able to explain. In 2009, researchers analysing the Fermi data noticed something unexpected. The telescope was detecting more gamma-ray emission from the inner region of the Milky Way than the models predicted. Not dramatically more, not an obvious flare or burst. A steady, diffuse, roughly spherical glow of gamma radiation centered approximately on the galactic center, extending several degrees outward on the sky, corresponding to a physical region a few thousand light-years across. This surplus became known as the galactic center giga-electron volt excess, named for the energy range where the signal is strongest, peaking around 1 to 3 GeV. The excess accounts for roughly 2% of all the gamma-ray emission in a broad circle around the galactic center. That might sound negligible, but in gamma-ray astrophysics, 2% of the total flux from the brightest region of the entire sky is an enormous amount of unexplained energy. To put it another way, the excess represents billions of times the total energy output of our Sun, arriving continuously from the direction of the galactic center in the form of high-energy photons that no identified source is producing. Models of galactic gamma-ray emission account for known sources. Cosmic rays, high-energy protons and electrons racing through the galaxy at nearly the speed of light, strike interstellar gas atoms and produce gamma rays through a process called pion decay. Individual pulsars emit gamma rays from their magnetospheres. Supernova remnants accelerate particles that radiate gamma rays as they interact with surrounding material. The dense interstellar radiation field near the galactic center provides a bath of low-energy photons that can be boosted to gamma-ray energies when struck by relativistic electrons through inverse Compton scattering. All of these contributions are understood, modeled, and subtracted from the observed signal. When you remove them, a residual remains. That residual is the excess. And as of 2026, after more than a decade and a half of study, nobody has been able to definitively explain what produces it. 3 competing explanations have dominated the debate. The first, and the most exciting, is dark matter annihilation. Dark matter makes up roughly 85% of all matter in the universe. It does not emit light, absorb light, or interact with electromagnetic radiation in any detectable way. Its presence is inferred entirely from gravitational effects, the rotation curves of galaxies, the bending of light around massive clusters, the large-scale structure of the cosmic web. Despite decades of effort, no experiment has directly detected a dark matter particle. Its identity remains one of the deepest open questions in all of physics. But if dark matter consists of weakly interacting massive particles, often abbreviated as WIMPs, a leading theoretical candidate, then under certain conditions those particles could annihilate when they collide with each other, converting their mass into energy that would include gamma rays. The process would work like this. 2 dark matter particles meet in the dense gravitational well of the galactic center. They annihilate, producing a cascade of standard model particles that includes, among other products, gamma-ray photons. The rate of annihilation depends on the square of the dark matter density, meaning that it increases dramatically in regions where dark matter is most concentrated. The galactic center is the place in the Milky Way where dark matter density is expected to be highest. If dark matter annihilation produces gamma rays, the strongest signal should come from the galactic core, and the spectral shape and spatial distribution of the GeV excess are broadly consistent with what models of dark matter annihilation predict for particles, with masses in the range of roughly 30 to 50 GeV. This possibility generated enormous excitement when it was first proposed. A confirmed gamma-ray signal from dark matter annihilation would be one of the most important discoveries in the history of physics. It would identify the particle nature of dark matter, constrain its mass and interaction properties, and open an entirely new window into the invisible majority of the universe's mass. Papers were published arguing that the GeV excess was the strongest indirect evidence for dark matter annihilation ever observed. The signal seemed to fit the theoretical predictions almost too well. The spectral shape matched. The spatial distribution matched. The required dark matter particle mass fell within the range that other experiments were already searching. For a few years, the gamma-ray excess looked like it might be the breakthrough that dark matter physicists had been waiting for. But there was a problem. The same signal could be produced by something far less exotic. The second explanation involves an unresolved population of millisecond pulsars. Pulsars are rapidly spinning neutron stars, the collapsed remnants of massive stars that have exhausted their nuclear fuel A neutron star packs roughly 1.5 solar masses into a sphere the size of a city, roughly 20 kilometers across. The density is so extreme that a single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. Some neutron stars spin at astonishing rates. Millisecond pulsars rotate hundreds of times per second, their surfaces whipping around at a significant fraction of the speed of light. These objects are known gamma-ray emitters. The powerful magnetic fields anchored to their surfaces accelerate particles to extreme energies, producing beams of radiation that include gamma rays. If the galactic center hosts a large population of old millisecond pulsars, too faint to be detected individually, their combined gamma-ray emission could produce a diffuse glow that mimics the GeV excess. No single pulsar would be bright enough to show up as a point source in the Fermi data. But thousands of them, blended together into a smooth, unresolved background, could produce exactly the kind of steady, extended emission that the excess represents. The spectral shape of known millisecond pulsar emission is similar to the observed excess. The spatial distribution could also match if the pulsar population follows the distribution of old stars in the galactic bulge, the dense, roughly spherical concentration of stars surrounding the galactic center. A key study published in 2018 by a team using advanced modeling of the galactic bulge's stellar structure argued that the GeV excess is spatially correlated with the X-shaped stellar overdensity in the Milky Way's bulge and with the nuclear stellar bulge at the very center. The Milky Way's bulge is not a smooth, featureless blob. Infrared surveys have revealed that it has a boxy, peanut-shaped structure when viewed from certain angles, with an X-shaped pattern of stars created by orbital resonances over billions of years. This correlation, the researchers argued, strongly suggests that the excess emission is produced by a stellar population rather than by dark matter, because dark matter is expected to follow a smooth, spherically symmetric distribution rather than the boxy, X-shaped morphology of the bulge stars. If the gamma rays trace the stars rather than the dark matter, pulsars become the more natural explanation. But this did not settle the argument. Other researchers pushed back, noting that the spatial morphology of the excess depends sensitively on how you model the known gamma-ray foregrounds. The galactic center is the brightest and most complicated region of the gamma-ray sky. Cosmic rays interact with dense gas in the central molecular zone. Individual point sources contribute overlapping emission. The interstellar radiation field is intense. Subtracting all of these components cleanly enough to isolate the excess requires assumptions about gas distribution, cosmic ray propagation, and source populations that carry significant uncertainties. Different modeling choices produce different residual morphologies. Depending on which foreground model you trust, the excess can look more like dark matter or more like pulsars. This modeling sensitivity is not a minor technicality. It is the core of the problem. The galactic center is the most complex region of the gamma-ray sky because it has the highest density of sources, the most intense backgrounds, and the most complicated interstellar medium. Separating the excess from the foreground is like trying to hear a quiet conversation in a crowded stadium. You know there is a voice you cannot account for, but depending on how you filter the crowd noise, the voice changes its apparent character. Some filters make it sound like a single speaker, others make it sound like a chorus. The excess is real, but its interpretation depends on assumptions that remain contested. The third explanation is perhaps the most intriguing from the perspective of galactic center science. Some researchers have proposed that the GeV excess is not produced by a steady source at all, but is instead a relic of a past energetic outburst from the galactic center. If Sagittarius A star experienced a period of significantly enhanced accretion activity roughly 1 million years ago, the resulting burst of energy could have injected high-energy electrons into the surrounding environment. Those electrons, interacting with the ambient radiation field through inverse Compton scattering, a process in which a fast-moving electron collides with a low-energy photon and boosts it to much higher energies, would produce gamma-ray emission that could persist for hundreds of thousands to millions of years after the original event. The timescale, the energy budget, and the spatial extent of such a scenario are broadly consistent with the observed GeV excess. This idea connects to other evidence suggesting that Sagittarius A star was far more active in the recent past than it is today. The black hole's current accretion rate is remarkably low. It consumes matter at a rate billions of times lower than the theoretical maximum for its mass. If you calculate how much energy Sagittarius A star should produce, given the amount of gas available in its vicinity, the answer is millions of times higher than what is actually observed. The black hole is, by the standards of active galactic nuclei, essentially asleep. But several lines of evidence suggest it was not always this quiet, and the strongest evidence for that past activity is visible on a much larger scale. Before we get to that evidence, though, we need to confront the anomaly that makes the gamma-ray excess even more uncomfortable: the missing pulsars. If the GeV excess is produced by millisecond pulsars, there should be a lot of them in the galactic center. Models estimate that hundreds of pulsars should be detectable within the central few hundred parsecs. The galactic center is dense with massive stars, many of which will eventually end their lives as neutron stars. The region has been forming stars for billions of years. The accumulated population of dead stellar remnants should be enormous. Pulsars in particular should be abundant because they are the natural end state of stars between roughly 8 and 25 solar masses. These stars burn through their nuclear fuel in millions of years, collapse in supernova explosions, and leave behind neutron star remnants that can spin and emit radio pulses for billions of years. In a region that has been forming stars continuously, the graveyard of dead stars should be deep, but when astronomers look for them, they are almost entirely absent. As of 2026, only one confirmed young pulsar has been detected within the central parsec, a magnetar designated J1-745-2-900, discovered in 2013. A magnetar is a special type of neutron star with an extraordinarily powerful magnetic field, thousands of times stronger than typical pulsars. While it is technically a member of the pulsar family, it is not the kind of ordinary radio pulsar that models predict should populate the galactic center by the hundreds. Beyond this single magnetar, a 2026 study by the Breakthrough Listen project at Columbia University identified a candidate millisecond pulsar in the galactic center region, but the candidate has not been confirmed in follow-up observations, and the researchers themselves described the detection with a mixed degree of confidence. The paper noted that the non-detection of pulsars in subsequent observations reinforces the ongoing missing pulsar problem, suggesting that strong scattering of radio signals by the dense interstellar medium near the galactic center, extreme orbital dynamics, or some other mechanism may be obscuring pulsar signals in this region. This is a real puzzle, and to understand why it is so stubborn, you need to understand what scattering does to pulsar signals. Pulsars are detected by their regularity. A typical pulsar emits a sharp pulse of radio emission once per rotation, and the pulse arrives at our telescopes with clockwork precision. This regularity is what allows astronomers to identify a pulsar against the noisy background of radio emission from the galaxy. But radio waves travelling through ionized gas are scattered. The scattering smears out the sharp pulse in time, turning a crisp spike into a broad, blurry bump. If the scattering is severe enough, the pulse becomes so smeared that it blends into the background noise, and the pulsar becomes undetectable. The galactic center has the densest, most turbulent ionized medium of any region in the Milky Way. Radio waves passing through this medium experience extreme scattering, far worse than in any other direction on the sky. The scattering effect is frequency dependent. It is worst at low radio frequencies and diminishes at higher frequencies, following a steep power law. This is why searches for galactic center pulsars have increasingly been conducted at higher frequencies where scattering is reduced. At sufficiently high observing frequencies, the scattering should become manageable, but even at these higher frequencies, pulsars remain elusive. Some researchers have argued that the scattering medium near the galactic center is more severe than standard models predict, with dense, turbulent clumps of ionized gas that produce extreme scatter even at high frequencies. Others argue that the scattering models are approximately correct, and that the pulsars genuinely are not there in the expected numbers. The distinction matters enormously. If scattering is the sole explanation, then the pulsars are present but hidden, and the pulsar explanation for the GeV excess remains viable. Future instruments with greater sensitivity and higher observing frequencies, particularly the square kilometre array, should be able to cut through the scattering and detect the hidden population. But if the pulsars are genuinely absent, something has destroyed them or prevented their formation, and the implications extend far beyond gamma-ray astronomy into fundamental physics. One provocative hypothesis connects the missing pulsars directly to dark matter. If dark matter particles accumulate inside neutron stars over time, drawn inward by the neutron star's intense gravity, they could eventually reach a critical density and collapse into a tiny black hole at the neutron star's core. That black hole would then consume the neutron star from the inside, destroying it. In the galactic center, where dark matter density is expected to be highest, this process would be most efficient. Pulsars would be destroyed faster than anywhere else in the galaxy, and the oldest pulsars would be the first to vanish. The result would be a galactic center largely emptied of old millisecond pulsars, with only the youngest pulsars surviving for a time before they too are consumed. This idea is speculative. It requires specific properties of dark matter particles that have not been confirmed, including a particular type called asymmetric dark matter that accumulates rather than annihilates. But if it were correct, it would simultaneously explain the missing pulsars and undermine the pulsar explanation for the GeV excess. If the pulsars have been destroyed by dark matter, they cannot be producing the gamma rays, and if they are not producing the gamma rays, the dark matter annihilation explanation regains strength. The researchers who proposed this scenario also made a testable prediction. The maximum age of pulsars should increase with distance from the galactic center, because the dark matter density drops as you move outward. Close to the center, pulsars would be destroyed quickly. Farther out, they could survive longer. This gradient should be detectable with sufficiently sensitive pulsar surveys. The circularity of this reasoning illustrates why the galactic center is so frustrating for physicists. Every proposed explanation for one anomaly either depends on or conflicts with the explanation for another anomaly. The gamma-ray excess, the missing pulsars, and the dark matter distribution are all entangled in a web of competing models that resist clean resolution. If the pulsars explain the excess, they should be findable. If they are not findable because of scattering, we cannot rule them out. If they are not findable because dark matter destroyed them, the dark matter explanation for the excess strengthens. But confirming that dark matter destroyed the pulsars requires understanding the dark matter density profile, which is itself uncertain and model-dependent. You cannot pull on one thread without tugging all the others. Now we need to step back. Literally, because the next anomaly associated with the galactic center is not measured in parsecs or even kiloparsecs. It is measured in tens of thousands of light years, and it was discovered not by looking at the galactic center, but by looking above and below it. In 2010, researchers working with data from the Fermi Gamma Ray Space Telescope announced the discovery of two enormous structures extending above and below the galactic plane. Each structure stretched roughly 25,000 light-years from the center of the galaxy, forming a pair of roughly symmetrical lobes or bubbles of gamma-ray emission. They were named the Fermi bubbles, and their discovery was completely unexpected. No model of the Milky Way's gamma-ray emission had predicted them. They simply appeared in the data once researchers developed new techniques to subtract the bright diffuse foreground of the galactic plane and look at what remained. The Fermi bubbles are enormous. Their combined height, from the top of one bubble to the bottom of the other, spans roughly 50,000 light-years, comparable to the radius of the galactic disk itself. To visualize their scale, imagine the flat disk of the Milky Way as a dinner plate. The Fermi bubbles would be two balloons, each as tall as the plate is wide, inflated from the center and extending straight up and down from the plate's surface. They dominate the gamma-ray sky at high galactic latitudes, and yet they were not discovered until 2010 because their emission is relatively soft compared to the bright galactic plane, and because isolating them required careful foreground subtraction. Their edges are remarkably sharp, suggesting they are bounded by some kind of shock front or discontinuity rather than gradually fading into the surrounding medium. A sharp edge is physically significant. It means something is confining the bubbles, separating the hot, energetic material inside from the cooler, quieter medium outside. Shock fronts form when material plows into its surroundings faster than the speed of sound in that medium, piling up a wall of compressed gas at the boundary. The sharpness of the Fermi bubble edges tells us that whatever created them did so with considerable violence, driving material outward at speeds fast enough to shock the galaxy's halo gas. Their gamma-ray spectrum is relatively uniform across their extent, with a hard spectral index that distinguishes them from the softer diffuse emission of the galactic plane. This uniformity is itself a puzzle. If the bubbles were inflated by a single explosive event millions of years ago, you might expect the gamma-ray spectrum to vary with distance from the center, with older, more distant regions showing softer spectra as the energetic particles lose energy over time. The relative uniformity suggests either that the particles are continuously re-accelerated throughout the bubble volume, perhaps at the shock boundary itself, or that the injection event was recent enough that significant energy loss has not yet occurred. And they are symmetrical about the galactic center, strongly suggesting that whatever created them originated from the core of the galaxy. Asymmetric explosions, off-center star formation events, or random supernova activity would not produce such clean bilateral symmetry. The bubbles point directly back to the galactic center like two columns of smoke rising from a single chimney. The origin of the Fermi bubbles remains under active debate. The two leading categories of explanation are an outburst from Sagittarius A star during a past period of enhanced accretion, and a sustained wind driven by intense star formation in the central molecular zone. In the black hole outburst scenario, Sagittarius A star experienced a phase of active galactic nucleus-like behavior millions of years ago, launching jets or wide-angle winds that inflated the bubbles. Many galaxies in the universe show evidence of powerful jets driven by their central black holes, jets that extend thousands or millions of light-years and blow enormous cavities in the surrounding gas. If Sagittarius A star produced even a brief, modest version of such activity, it could have inflated the structures we observe. In the star formation wind scenario, the concentrated population of massive stars in the galactic center drives a collective superwind through the combined effect of stellar winds and supernova explosions. Massive stars burn through their fuel quickly and die violently. In a region where many massive stars are forming and dying simultaneously, the cumulative energy output can drive a sustained outflow of hot gas perpendicular to the galactic plane. This superwind would inflate bubble-like structures in the halo over millions of years. The central molecular zone has enough star formation activity to plausibly power such a wind, though the exact energy budget is debated. Both scenarios face challenges. The black hole outburst model must explain why the bubbles have persisted for millions of years after the event that created them, and it must match the observed energy budget, estimated at roughly 10 to the 55th to 10 to the 57th ergs. A 2025 paper proposed that tidal disruption events, in which Sagittarius A star tears apart and consumes entire stars that wander too close, could have provided the necessary energy through repeated episodes over millions of years. Each tidal disruption would produce a brief flare of accretion activity, launching material outward. Accumulated over many events, these flares could collectively inflate the bubbles without requiring a single dramatic episode. A separate 2025 simulation study using three-dimensional magnetohydrodynamic models proposed a double-episode jet scenario in which two separate outbursts from the black hole at different times created the nested bubble structure that observations reveal. In this picture, an older, more powerful jet inflated the outer structures roughly 15 million years ago, while a younger jet, roughly 5 million years ago, created the inner structures, producing the layered configuration we observe today. Because the Fermi bubbles are not alone. In 2020, the Rosetta X-ray telescope aboard the Spectrum Röntgen Gamma Observatory revealed an even larger pair of structures. The Rosetta bubbles extend to roughly 80 degrees above and below the galactic center, corresponding to a physical height of approximately 40 to 45,000 light-years on each side. These X-ray bubbles are larger than the Fermi bubbles and appear to enclose them, creating a nested configuration in which the gamma-ray Fermi bubbles sit inside the larger X-ray Rosetta bubbles. The discovery was made from the first all-sky X-ray survey conducted by the observatory, and like the Fermi bubbles before them, The A-Rho-Zeta structures had no precedent in theoretical predictions. They simply appeared in the data as enormous, symmetrical, sharply bounded regions of enhanced X-ray emission flanking the galactic center. The morphological similarity between the two sets of bubbles is striking. Both are roughly symmetrical about the galactic plane. Both appear centered on the galactic center. Both have relatively sharp edges. The nesting suggests a physical relationship, as if the same central engine produced both structures, with the Fermi bubbles representing a more recent or more energetic inner component, and the A-Rho-Zeta bubbles representing an older or more diffuse outer shell. But the bubble structures do not stop at gamma rays and X-rays. They have counterparts across the electromagnetic spectrum in a way that is itself one of the most remarkable features of the galactic center anomaly environment. The A-Rho-Zeta bubbles have counterparts in radio wavelengths, where polarized emission reveals giant radio lobes aligned with the bubble structures. These radio lobes were detected even before the A-Rho-Zeta discovery, but their connection to the larger bubble system only became clear once the X-ray data revealed the full extent of the structures. In microwave wavelengths, a feature called the microwave haze, first detected by the WMAP satellite and later confirmed by the Planck spacecraft, appears to fill roughly the same region as the Fermi bubbles. The haze is an excess of microwave emission above what standard models of galactic synchrotron and dust radiation predict. Its spectrum is consistent with synchrotron emission from a population of high-energy electrons, the same kind of electrons that could produce the gamma-ray emission of the Fermi bubbles through inverse Compton scattering. The multi-wavelength nature of the bubble system is critically important. It means the bubbles are not a single wavelength artifact or a subtle foreground subtraction error. They are real, physical structures detected independently by different telescopes using completely different technologies, observing in completely different parts of the electromagnetic spectrum. Radio telescopes see the polarized synchrotron emission. Microwave satellites see the haze. Gamma-ray space telescopes see the Fermi bubbles. X-ray observatories see the A-Rho-Zeta shells. Each detection uses different physical processes and different instrumentation. The fact that they all point to the same structures, originating from the same central location, with consistent spatial morphologies, is powerful evidence that the bubble system is a genuine astrophysical phenomenon driven by processes at the galactic center. The galactic center is producing structured emission across nearly every observable wavelength, from radio through microwave, through X-ray, through gamma-ray, and all of it points upward and downward from the same central location. This is not normal galactic behavior. Most of the Milky Way's disk is relatively quiet at high latitudes. The halo gas above and below the plane is thin, faint, and uneventful. The galactic center is the one region punching through that quiet boundary and exporting enormous energy into the surrounding galaxy. The energy required to inflate the A-Rho-Zeta bubbles is staggering. Estimates suggest that the total energy content of the combined bubble system exceeds 10 to the 56 ergs and possibly reaches 10 to the 57 ergs. For comparison, a typical supernova releases approximately 10 to the 51 ergs. The combined bubble system contains the equivalent energy of tens of thousands to hundreds of thousands of supernovae, all apparently originating from the galactic center. Sustaining that energy output requires either a single catastrophic event or a continuous process operating over millions of years. Neither option is easy to explain with conventional models, and some models suggest the bubbles may not be transient structures at all. A 2024 study proposed that the Fermi and A-Rho-Zeta bubbles could be persistent features of the Milky Way, maintained over at least the past billion years by continuous outflows from the galactic disk, rather than by a single explosive event. In this picture, the bubbles are not relics of a past cataclysm. They are permanent exhaust plumes, constantly fed by the ongoing activity at the galactic center, as much a part of the galaxy's anatomy as the spiral arms or the central bar. If true, this would mean the galactic center has been pumping enormous energy into the surrounding galaxy for a significant fraction of cosmic history, reshaping the Milky Way's halo on scales that dwarf the disk itself. The nested bubbles add a critical dimension to the anomaly stack at the galactic center. The gravitational anomalies we explored earlier are confined to the central parsec, a tiny region dominated by Sagittarius A star's immediate influence. The GeV excess extends a few thousand light-years. But the Fermi and A Rosetta bubbles reach tens of thousands of light-years into the galactic halo, demonstrating that whatever processes operate at the galactic center do not stay confined to the center. The core of the galaxy is exporting energy, particles, and magnetic structures into the broader Milky Way on scales comparable to the galaxy's own diameter. The galactic center is not just locally anomalous, its influence extends across the entire galaxy, and here is where the layers start to press against each other. The GeV excess sits at the base of the Fermi bubbles. The physical relationship between them is uncertain but potentially significant. Some models suggest that the base of the Fermi bubbles, where they connect to the galactic plane, contributes gamma-ray emission that contaminates the measurement of the GeV excess. If the Fermi bubbles extend into the galactic center region at low latitudes, their emission must be accounted for when modeling the excess. Different assumptions about how the bubbles behave near the galactic plane produce different estimates of how much excess emission remains after subtraction. This uncertainty is one of the reasons the GeV excess debate has been so difficult to resolve. You cannot cleanly measure the excess without understanding the bubbles, and you cannot fully understand the bubbles without knowing what drives them, and the candidates for what drives them include the same black hole and the same stellar populations that are implicated in the excess itself. The missing pulsars sit in the middle of all of this. If a large population of millisecond pulsars exists in the galactic center, they could contribute to the GeV excess, and they should be detectable as individual radio sources if scattering were not obscuring them. But if they are genuinely absent, destroyed by dark matter accumulation or never formed in the expected numbers because of the extreme environment, then the GeV excess loses its most conventional explanation, and the galactic center becomes even harder to model. And if the pulsars are missing because magnetar formation is preferentially favored in the galactic center, as one study has proposed, that raises its own set of questions about the stellar evolution and magnetic field conditions in the region. In the broader galaxy, ordinary pulsars outnumber magnetars by large factors. If the galactic center preferentially produces magnetars instead, the intense magnetic fields of the region may be influencing the end states of dying stars in ways not accounted for by standard stellar evolution theory. Every thread connects to every other thread. The gamma-ray excess depends on the pulsar population. The pulsar population depends on stellar evolution in extreme environments. Stellar evolution depends on the formation history of stars near the black hole, which links back to the paradox of youth. The Fermi bubbles depend on the energy output of the galactic center over millions of years. That energy output depends on whether the black hole was more active in the past, and the evidence for past activity connects to the same magnetic field structures that the EHT revealed around Sagittarius A star in polarized light. This is not a collection of isolated curiosities. It is an interconnected web of anomalies, each one feeding uncertainty into the next, all of them rooted in the same small region at the center of the Milky Way. And we have not yet touched the most visually spectacular and perhaps most mysterious layer of all. The galactic center is threaded with nearly 1,000 magnetic structures that have no parallel anywhere else in the galaxy. For decades, only a few dozen were known. When the newest radio telescopes finally mapped the full population, the sheer number of them transformed a decades-old curiosity into something that demanded immediate attention. The magnetic structures of the galactic center are the next layer, and they are about to make the picture significantly stranger. In 1984, a young astronomer named Farhad Yousefzadeh, working with Mark Morris and Don Chance, pointed a radio telescope at the center of the Milky Way and found something that nobody expected. Stretching across the field of view, running roughly perpendicular to the flat plane of the galaxy, were long, thin, luminous threads of radio emission. They were strikingly straight. They were narrow, some barely a fraction of a parsec across, and they were tall, extending tens of parsecs in length, standing upright against the galactic disk like the bars of an enormous cage surrounding the galactic core. Nobody knew what they were. The emission was clearly non-thermal. It was not produced by hot gas radiating because of its temperature. It was synchrotron radiation, the kind of light created when electrons moving at nearly the speed of light spiral around magnetic field lines. To produce synchrotron emission, you need two things: a magnetic field and a population of electrons traveling at relativistic speeds. The electrons, trapped by the field, are forced to curve along helical paths. Charged particles that change direction radiate energy. When the particles are moving close to the speed of light, the radiation they emit is concentrated into a narrow beam and boosted to high frequencies. The result is a distinctive type of emission with specific polarization and spectral properties that allows astronomers to identify it unambiguously. The threads in the galactic center were glowing in synchrotron radiation, which meant they were magnetic structures. Highly ordered, intensely magnetized tubes of plasma, glowing in radio wavelengths because relativistic electrons were trapped inside them and forced into spiraling paths by the magnetic field. The field strengths inferred from the emission and from Faraday rotation measurements, the twisting of the polarization angle of light as it passes through a magnetized medium, were enormous by galactic standards. Estimates range from fractions of a milligauss to a full milligauss, tens to hundreds of times stronger than the typical magnetic field in the Milky Way's disk. In the neighborhood of our solar system, the galactic magnetic field measures only a few microgauss, roughly 10 million times weaker than a refrigerator magnet, but strong enough to influence the paths of cosmic rays over thousands of light years. The filaments at the galactic center existed in a magnetic environment that dwarfed anything in the broader galaxy. For nearly 4 decades after their discovery, the radio filaments of the galactic center remained a curiosity. A few dozen were known. They were studied individually, catalogued, debated. Theories were proposed for their formation. Some researchers suggested they were produced by the interaction between large-scale poloidal magnetic fields running perpendicular to the galactic plane, and the turbulent motions of gas clouds in the central molecular zone. Others proposed that the filaments were illuminated by streams of cosmic ray electrons, escaping from specific sources like supernova remnants or the vicinity of Sagittarius A star itself. Still others suggested magnetic reconnection events, in which field lines snap and reconfigure, releasing bursts of energy that accelerate electrons along specific magnetic tubes. None of these explanations became consensus. The filaments were too few and too poorly characterized to discriminate between models. Then, MeerKAT changed everything. MeerKAT is a radio telescope array operated by the South African Radio Astronomy Observatory, located in the Karoo region of South Africa. It consists of 64 dish antennas working together as an interferometer, and its sensitivity and resolution at radio wavelengths represent a generational leap over previous instruments. In early 2022, a team led by Ian Haywood published a stunning mosaic image of the galactic center at a frequency of 1.28 GHz. The image covered a broad swath of the inner galaxy with unprecedented clarity and depth. The observation represented hundreds of hours of telescope time combined into a single composite, revealing the radio sky toward the galactic center at a level of detail that had simply not been available before. What emerged from the data was staggering. Instead of the few dozen filaments previously catalogued, the MeerKAT image revealed nearly 1,000 individual magnetized threads concentrated in the galactic center region. They appeared in pairs and clusters. Some were stacked side by side with remarkably uniform spacing, like the strings of an instrument no one had built. Others stood in isolation, solitary lines of radio emission cutting through the chaotic background of the galactic plane. Some stretched over 150 light-years in length while maintaining widths of less than 1 light-year. The aspect ratios were extreme, like finding a wire thin enough to thread through a needle yet long enough to stretch from one city to another. The MeerKAT mosaic also revealed other features that added to the complexity. Radio-emitting bubbles roughly 1,400 light-years across appeared at the center, straddling Sagittarius A star. These were not the Fermi bubbles, which are vastly larger. They were a separate, smaller-scale structure nested within the central region, visible only in radio wavelengths. Supernova remnants dotted the field, some previously known and others newly discovered. Compact star-forming regions glowed amid the chaos. The full image was a portrait of the galactic center as a radio environment of extraordinary richness and complexity, but the filaments dominated the conversation. The meerkat image did not just increase the number of known filaments, it transformed the scientific conversation. A few dozen filaments could be treated as individual oddities, local accidents of magnetic field geometry. Nearly 1,000 filaments organized into coherent populations demanded a systemic explanation. Something about the galactic center environment was producing these structures at scale, and whatever that something was, it did not operate anywhere else in the Milky Way. No other region of the galaxy hosts anything comparable. The filaments are unique to the galactic center. Youssef Zardeh and collaborators followed up the meerkat mosaic with detailed statistical analyses of the filament population. They measured spectral indices, the way the radio brightness changes across different frequencies, for hundreds of filaments. They found that the filaments fall into distinct spectral categories, suggesting that more than one physical mechanism may be responsible for producing them. Some filaments had steep spectral indices, meaning their emission fades rapidly at higher frequencies, consistent with older populations of cosmic ray electrons losing energy over time. Others had flatter spectra, suggesting more recent acceleration, or a continuous supply of fresh, energetic particles. The existence of distinct spectral populations within the same physical region raises the possibility that the filaments are not a single phenomenon, but a family of related structures produced by overlapping processes. The magnetic field strengths derived from equipartition arguments, a method that balances the energy in relativistic particles against the energy stored in the magnetic field, ranged from roughly 50 to over 100 microgauss for typical filaments. These values are far above the few microgauss fields measured in the general interstellar medium of the Milky Way's disk. Even in the spiral arms, where magnetic fields are somewhat enhanced by compression and turbulence, field strengths rarely exceed 10 microgauss. The filaments inhabit a magnetic environment that is an order of magnitude more intense than anything found in the broader galaxy. But the vertical filaments were only part of the story. In June of 2023, Youssef Zardeh and collaborators published another discovery. Amid the forest of vertical threads, they found a population of horizontal filaments, short dashes of radio emission lying parallel to the galactic plane, rather than perpendicular to it. These horizontal filaments were smaller than their vertical counterparts, typically a few light years long, and they appeared concentrated in the inner region near Sagittarius A star. Their orientation was completely different from the vertical population. Vertical filaments trace a large-scale poloidal magnetic field, one that runs perpendicular to the disk. Horizontal filaments suggest a toroidal component, a field running along the plane, or possibly a localized phenomenon driven by outflows or winds from the central region. The discovery of two distinct populations of filaments running in different directions complicated the picture considerably. A single large-scale magnetic field geometry cannot easily explain both orientations. The vertical filaments had been tentatively attributed to a global poloidal field threading the galactic center, a relic of the galaxy's formation, or a structure maintained by large-scale currents in the interstellar medium. The horizontal filaments pointed toward additional processes operating on smaller scales, possibly connected to outflows from Sagittarius A star, to stellar winds from the massive star clusters in the region, or to the interaction between the large-scale field and the dense, turbulent gas of the central molecular zone. The central molecular zone itself is a critical part of the magnetic puzzle, and it deserves careful attention because it is the physical stage on which much of the galactic center drama unfolds. This is a roughly elliptical ring of dense molecular gas and dust surrounding the galactic center, extending roughly 300 parsecs along the galactic plane and about 30 parsecs in height. It contains an estimated 30 to 60 million solar masses of molecular hydrogen, making it the largest concentration of dense gas in the galaxy. By mass, the central molecular zone holds roughly 5 to 10% of all the molecular gas in the entire Milky Way, packed into a volume that represents a tiny fraction of the galactic disk. This concentration of gas should make the central molecular zone a furious engine of star formation. Dense gas collapses under gravity to form new stars. The denser the gas, the faster the collapse, and the more stars you produce. In the outer galaxy, regions with comparable gas densities form stars at predictable rates that match empirical scaling laws developed from observations of thousands of molecular clouds. But the central molecular zone defies these laws. Its star formation rate is roughly 10 times lower than what the gas density alone would predict. This discrepancy is called the star formation deficit, and it has puzzled researchers for years. The magnetic field provides a plausible explanation. If the field strength in the central molecular zone is high enough, magnetic pressure can support gas clouds against gravitational collapse, effectively putting a brake on star formation. A magnetic field resists compression. Gas trying to collapse must first push against the magnetic pressure, which requires more energy than gravity alone provides in marginally stable clouds. Measurements suggest that the magnetic pressure in the central molecular zone is comparable to or even exceeds the turbulent kinetic pressure of the gas, a condition that is essentially never met in the broader galactic disk. This makes the central molecular zone one of the only regions in the Milky Way where magnetism is a dominant force in the dynamics of interstellar gas. But this raises its own questions. What maintains such a strong magnetic field in the central molecular zone? The field must be either continuously generated by local dynamo processes, fed by currents in the ionized gas, or it must be a relic of the galaxy's formation that has been amplified by the compression of gas flowing inward toward the galactic center. Each of these possibilities is physically plausible but not confirmed, and the relationship between the central molecular zone's internal magnetic field and the spectacular radio filaments that stand above and around it remains unclear. The filaments may be part of the same large-scale magnetic structure, with the vertical threads representing field lines that extend above the dense gas into the more diffuse medium of the galactic halo. Or they may be separate structures, produced by different mechanisms and only spatially coincident because both are anchored to the same gravitationally extreme region. The overall picture is one of magnetic complexity without any known precedent in the Milky Way. The galactic center contains ordered magnetic fields strong enough to influence the dynamics of interstellar gas. Structured into populations of filaments with distinct orientations and spectral properties, embedded in a broader environment of extreme turbulence, intense radiation, and powerful gravitational fields. The magnetic energy density in this region is comparable to the kinetic energy density of the gas, meaning that magnetism is not a passive bystander in the galactic center. It is an active player, shaping how matter moves, how gas collapses, and how energy propagates through the region. One particular filament has drawn outsized attention. The thread designated G0.17-0.41 was identified in observations that combined data from both the Chandra X-ray Observatory and Meerkat. This filament is unusual because it emits in both radio and X-ray wavelengths. Most of the radio filaments in the galactic center are detected only at radio frequencies. Finding one that also glows in X-rays suggests a different or additional physical process is at work. The leading interpretation is magnetic reconnection, the same process that drives solar flares on our own sun but operating on vastly larger scales. In magnetic reconnection, oppositely directed magnetic field lines are driven together, often by the motion of surrounding plasma. When the field lines come close enough, they snap and reconnect in a new configuration, releasing stored magnetic energy as heat, particle acceleration, and radiation. On the Sun, reconnection events produce flares lasting minutes to hours and release energies of roughly 10 to the 25th to 10 to the 32 ergs. In the galactic center, a reconnection event powerful enough to produce detectable X-ray emission from a filament tens of light-years long would involve enormously more energy, operating in magnetic fields orders of magnitude stronger than the solar corona and sustained over far longer timescales. If magnetic reconnection is occurring in the galactic center at the scales implied by G0.17-0.41, it has implications for the broader energy budget of the region. Reconnection converts magnetic energy into particle energy, accelerating electrons to relativistic speeds. Those accelerated electrons would then radiate synchrotron emission as they spiral through the ambient magnetic field, contributing to the non-thermal radio glow of the galactic center. They could also inverse Compton scatter ambient photons to higher energies, potentially contributing to the gamma-ray emission observed by the Fermi telescope. In other words, magnetic reconnection could be a hidden energy source feeding multiple observable phenomena in the galactic center. connecting the magnetic anomalies to the radiation anomalies discussed earlier. The energy stored in the galactic center's magnetic field is enormous. If even a fraction of it is being released through reconnection events distributed across the filament population, the total energy contribution could be significant enough to matter for the region's overall energy balance. But the magnetic structures are not the only mysterious signals emerging from the galactic center. There is another category of anomaly that exists at the intersection of radio astronomy and the unknown. These are the galactic center radio transients. In the early 2000s, astronomers detected a small number of radio sources near the galactic center that appeared, brightened, and then vanished without matching the behavior of any known class of astronomical object. These sources were given the designation GCRT for Galactic Center Radio Transient. Only a handful were confirmed in the initial detections. They shared certain properties. They were transient, appearing and disappearing on timescales of hours to weeks. They were highly polarized, meaning their radio emission was organized in a way that suggests a strong magnetic field at the source. And they had no counterpart at other wavelengths. No X-rays, no infrared emission, no optical signal, just a radio source that turned on, shone brightly, and then turned off. The absence of multi-wavelength counterparts is what makes the GCRT sources so difficult to classify. In modern astrophysics, classification of transient sources relies heavily on matching behavior across the electromagnetic spectrum. A magnetar outburst produces both radio and X-ray emission. A stellar flare produces radio, optical, and sometimes X-ray emission. An X-ray binary produces correlated variability across radio, optical, and X-ray bands. When a transient source appears in only one wavelength band, with no detectable counterpart in any other, the standard classification framework breaks down. You cannot match the object to any known category because every known category predicts multi-wavelength signatures that the source does not exhibit. The object falls through the taxonomic grid. The GCRT sources were strange, but with only a few detections they could be dismissed as statistical oddities or instrumental artifacts. That changed when the Australian Square Kilometre Array Pathfinder, known as ASCAP, began its surveys. Between April of 2019 and August of 2020, ASCAP detected a new source designated ASCAP-J 173608 in the direction of the galactic center. The source appeared 13 times during the survey period, never lasting more than a few weeks before vanishing. Its radio emission was highly polarized, consistent with the known GCRT sources, but its behavior also differed from the earlier detections in important ways. The known GCRT sources appeared and disappeared on timescales of hours. ASCAP J173608 lingered for weeks, then vanished abruptly, sometimes disappearing within a single day. Follow-up observations with the Meerkat telescope and the Australia Telescope Compact Array managed to redetect the source, but its behavior had changed dramatically between instruments and observation epochs. It was as if the source was deliberately eluding systematic study, changing its character every time a new telescope looked at it. The research team systematically ruled out known source types. Pulsars were excluded because the source lacked the regular periodicity that defines pulsar emission. Magnetars were excluded because there was no associated X-ray emission. X-ray binaries, gamma-ray bursts, and supernovae were all inconsistent with the observed properties. The source was located only about 4 degrees from the galactic center on the sky, placing it in the same general region as the known GCRT sources. The researchers acknowledged the similarity but also noted that the GCRT class itself is not understood. Linking ASCAP J173608 to the GCRT category does not explain it. It merely adds another member to a club whose membership requirements nobody can define. This classification failure points to something deeper. Astrophysical taxonomy works well when the physical processes producing observable signals are well understood. Stars, pulsars, magnetars, X-ray binaries, supernovae, gamma-ray bursts. Each of these source categories is grounded in specific physical models that predict what the source should look like across multiple wavelengths. When a new source is discovered, astronomers match its observed properties against these predictions and assign it to the appropriate category. The system works because the underlying physics is sufficiently well understood. But the GCRT sources and objects like ASCAP J173608 resist this process. They do not match any existing category. Their properties are inconsistent with every known source type. This either means they belong to a genuinely new class of object produced by physical processes not yet understood, or they represent extreme or unusual manifestations of known processes that standard models do not predict. Either possibility is scientifically significant, and either possibility becomes more interesting and more unsettling, because these sources keep appearing near the galactic center. What makes the galactic center radio transients especially unsettling is not any individual source, but the pattern. These signals are appearing preferentially in the direction of the galactic center. Whether this is because the galactic center genuinely produces a unique class of radio transient, or because the high stellar density and extreme conditions of the region create environments not found elsewhere in the galaxy, or because it is simply a coincidence of survey geometry, remains unknown. But the concentration of unexplained radio behavior near the galactic center fits the broader pattern that defines this entire story. Anomalies cluster here, not randomly, not in a way that distributes evenly across the galaxy. They concentrate in the same region where gravity is most extreme, where magnetic fields are strongest, where radiation is most intense, and where stellar densities are highest. The galactic center's magnetic environment also connects to the bubble structures explored earlier. The Fermi bubbles and the Rho-Z-Tar bubbles both show signatures of magnetic structure. Polarized radio emission along the edges of the bubbles indicates that magnetic fields are organized within the bubble walls, likely compressed and amplified by the shocks that define the bubble boundaries. The vertical radio filaments in the galactic center, which run perpendicular to the galactic plane, are aligned with the general direction of the bubbles. This alignment suggests a physical connection between the small-scale magnetic structures near Sagittarius A star and the enormous bubble structures extending tens of thousands of light-years into the halo. If a large-scale poloidal magnetic field threads the galactic center, it could serve as a conduit for energy and particles escaping the central region and inflating the bubbles. Cosmic rays accelerated by magnetic reconnection events, supernova shocks, or interactions with the black hole's magnetosphere could stream along these field lines, carrying energy far from the galactic plane and depositing it in the halo. The filaments in this picture are not just isolated curiosities. They are visible traces of the magnetic scaffolding that connects the galactic center to its largest scale outflows. The radio filaments would be the local expression of a field structure that, when followed outward, shapes the walls of the Fermi and Rho-Z-Tar bubbles tens of thousands of light-years away. This idea remains a hypothesis. The data do not yet definitively link the filaments to the bubbles through a single coherent magnetic structure, but the alignment, the field strengths, and the energy scales are all consistent. The vertical filaments, the horizontal filaments, the bubble walls, the radio lobes, and the microwave haze may all be different manifestations of the same underlying magneto-hydrodynamic system operating in the galactic center, a system in which magnetic energy, particle acceleration, and large-scale outflows are continuously generated, structured, and exported from the most extreme environment in our galaxy. The upcoming Square Kilometre Array, or SKA, currently under construction in South Africa and Australia, will bring radio sensitivity and resolution far beyond what Meerkat achieved. The SKA is expected to detect fainter filaments, resolve their internal structure, and potentially identify the mechanisms that create and maintain them. It will also conduct deep searches for pulsars in the galactic center, directly testing whether the missing pulsar problem is a scattering effect or a genuine population deficit. And it will enable systematic surveys for galactic center radio transients, determining whether these signals are truly concentrated in the galactic center or whether improved sensitivity reveals them across the galaxy. If the GCRT sources turn out to be a galactic center phenomenon, uniquely produced by the conditions in this extreme environment, they will become another entry on the growing list of things found nowhere else. If they turn out to be widespread, the galactic center connection was a coincidence, and the classification problem belongs to radio astronomy as a whole, rather than to galactic center science specifically. At every wavelength, at every scale, the galactic center refuses to behave the way the rest of the galaxy does. The magnetic field structures are unique. The radio transient population is unexplained. A star formation rate in the central molecular zone is suppressed by mechanisms that operate nowhere else. The connection between small-scale magnetic phenomena and large-scale bubble structures is suggestive but unresolved, and every new radio observation adds detail without providing closure. The galactic center is not yielding its secrets in an orderly sequence. It is revealing them all at once, in overlapping layers, each one complicating the last. Gravity, radiation, magnetism, signals. 4 independent categories of anomaly, observed across different wavelengths, measured by different instruments, studied by different research communities, and all of them pointing at the same patch of sky, all of them concentrating in a region smaller than 1% of the galaxy's total diameter, all of them straining the models that work perfectly well everywhere else. The question is no longer what scientists found at the galactic center. The question is why so many different kinds of anomalies keep piling up in the same place. That convergence, the repeated stacking of unresolved problems at a single astrophysical location, is the real reason this region is generating alarm. And it is the subject of what comes next. Imagine you are a doctor. A patient walks in complaining of a sore knee. You examine it, find some inflammation, prescribe rest and ice. Straightforward. The next week, the same patient returns. Now the knee is worse, but they also have unexplained fatigue. You run blood tests. The results are borderline, not alarming on their own, but not clean either. A month later, they are back again. The fatigue has deepened. A rash has appeared on their arms. Their blood work now shows anomalies in 3 separate systems, none of them dramatic enough to trigger an individual diagnosis, but all of them slightly off in ways that do not fit together under any single explanation. You are no longer treating a sore knee. You are staring at a cluster of symptoms that refuse to resolve into one clean disease. And the thing keeping you up at night is not any single reading. It is the fact that all of them are wrong at the same time, in the same patient, and none of your standard diagnostic frameworks can explain the full pattern. That is what is happening at the center of the Milky Way. Over the course of this story, we have walked through 4 distinct categories of anomaly, each one observed in different wavelengths of light, measured by different instruments, analyzed by different research communities, and published in different journals. The gravitational anomalies involve stars in orbits that defy formation models, objects surviving where tidal forces should destroy them, a binary system persisting where binaries should be torn apart, and orbital dynamics that reveal a mass distribution more complex and depleted than standard models predict. The radiation anomalies involve an unexplained gamma-ray excess that resists definitive attribution to either dark matter or pulsars, a missing population of dead stars that should be present by the hundreds, and a pair of nested bubble structures extending tens of thousands of light-years above and below the galactic plane, whose origin remains actively debated. The magnetic anomalies involve nearly 1,000 filaments of magnetized plasma unique to the galactic center, organized into at least 2 distinct populations with different orientations, embedded in a magnetic field environment an order of magnitude stronger than anything found in the wider galaxy. And the signal anomalies involve radio transients that match no known source category, appearing preferentially in the direction of the galactic center and vanishing without explanation. Taken individually, each of these anomalies is a legitimate scientific puzzle. Stellar dynamics near supermassive black holes are expected to be complex. Gamma-ray backgrounds are notoriously difficult to model. Magnetic field structures in dense environments are not fully understood anywhere. Radio transient astronomy is still a young field. If any one of these problems existed in isolation, it would be the subject of specialized research within its own subfield, pursued by dedicated teams, and would not necessarily generate broader alarm. But they do not exist in isolation. They all occur in the same place, within a region that, depending on which anomaly you are discussing, spans from a few parsecs to a few kiloparsecs around the exact center of the galaxy. The gravitational anomalies cluster within the central parsec. The gamma-ray excess extends a few kiloparsecs. The magnetic filaments fill the inner few hundred parsecs. The radio transients appear within a few degrees of the galactic center on the sky. The Fermi and Aero-Zetar bubbles erupt from the same central location. Everything points inward. Everything concentrates at the same address. This spatial convergence is what separates the galactic center from other astrophysical puzzles. The universe is full of unexplained observations. Fast radio bursts were a mystery for years. The accelerating expansion of the universe remains fundamentally unexplained. Dark matter has not been directly detected despite decades of searching. But these mysteries are distributed across the cosmos, arising from different environments and different physical regimes. The galactic center is different because it stacks multiple unrelated anomalies on top of each other in a single compact region. The anomalies do not share a common explanation. The stars orbiting Sagittarius A star have nothing obvious to do with the missing pulsars. The magnetic filaments are not directly related to the gamma-ray excess. The radio transients operate on time scales and energy scales that differ completely from the Fermi bubbles, yet all of them converge on the same location, as if the galactic center is a place where the universe's unresolved problems have agreed to meet. Why does this happen? The answer, or at least the beginning of an answer, lies in what makes the galactic center physically unique. It is one of the very few locations in the Milky Way where multiple extreme physical conditions overlap simultaneously. Consider what converges in this region. Extreme gravity. Sagittarius A star is the most massive compact object in the galaxy, and the gravitational field within the central parsec produces tidal forces, orbital velocities, and space-time curvature found nowhere else in the Milky Way. This extreme gravity does not just affect the stars orbiting the black hole, it shapes the dynamics of gas inflow, it determines where and how accretion occurs, and it sets the energy scale for any material that approaches the event horizon. Extreme stellar density. The galactic center hosts the highest concentration of stars in the galaxy. This density means more gravitational interactions between stars, more frequent stellar collisions, more supernova explosions per unit volume, and a more complex dynamical environment than any other region. The crowding also means that stellar evolution operates differently here. Stars interact with each other and with the black hole in ways that do not happen in the quiet outskirts where our solar system resides. Extreme radiation. The combination of massive young stars, supernova remnants, the black hole's accretion activity, and the dense interstellar radiation field creates a radiation environment that is intense across the entire electromagnetic spectrum. From radio through infrared, through X-ray, through gamma-ray, the galactic center is the brightest and most complex region of the sky. This radiation does not merely illuminate the region. It ionizes gas, accelerates particles, heats dust, and alters the chemistry of the interstellar medium. Extreme magnetism. As we explored earlier, the galactic center hosts magnetic field strengths an order of magnitude above the galactic average, structured into populations of filaments and organized into large-scale configurations that have no counterpart elsewhere. These fields are not passive. They influence gas dynamics, suppress star formation, accelerate particles to relativistic speeds, and may serve as conduits for energy transport over scales of tens of thousands of light years, and potentially extreme dark matter density. The galactic center is predicted by standard cold dark matter models to be the location of the highest dark matter concentration in the Milky Way. This concentration is what makes the region the prime target for indirect dark matter detection through annihilation signals. It is also what makes the missing pulsar problem potentially connected to dark matter physics. If dark matter density is truly as high as models predict, the inner galaxy becomes a place where dark matter effects on astrophysical objects could be measurable, something that is not possible anywhere else nearby. Each of these conditions, extreme gravity, extreme stellar density, extreme radiation, extreme magnetism, and potentially extreme dark matter concentration, is individually capable of pushing astrophysical models toward their limits. Standard models of star formation work well in quiet molecular clouds, but struggle near a supermassive black hole. Standard models of gamma-ray emission work well in the diffuse interstellar medium, but become ambiguous in the dense, source-rich environment of the galactic center. Standard models of magnetic field evolution work well in the galactic disk, but cannot easily explain the filament populations unique to the center. Standard models of pulsar populations work well in the broader galaxy, but fail to predict the absence of pulsars in the one region where they should be most abundant. When all 5 of these extreme conditions overlap in a single region, The result is not just one model being pushed to its limit, it is multiple models being pushed to their limits simultaneously. The galactic center is a place where the assumptions underlying several independent branches of astrophysics all become uncertain at once. And because the anomalies in each branch have not been resolved, the uncertainties compound. The gamma-ray excess cannot be cleanly measured without understanding the magnetic field structure. The magnetic field structure cannot be fully explained without understanding the energy input from the black hole and the stellar population. The stellar population cannot be reconciled with formation models without invoking specific dynamical histories. And the dark matter distribution, which could in principle help resolve the gamma-ray excess and the missing pulsars, remains unmeasured at the precision needed to discriminate between competing explanations. This is what the phrase model strain means in practice. It does not mean that physics is broken. It does not mean that general relativity has failed, or that dark matter has been disproven, or that our understanding of magnetic fields is fundamentally wrong. It means that in this one region, the simplifying assumptions that make astrophysical models tractable everywhere else break down. The models are not wrong, they are insufficient. They were built for environments where one or maybe two extreme conditions apply. In the galactic center, 5 apply at once, and the interactions between them create a complexity that existing frameworks were not designed to handle. This is why the word panic, while sensational in a headline, captures something real about the scientific mood. Researchers across multiple subfields are encountering the same pattern. Their models work well everywhere except at the galactic center. Stellar dynamicists find orbits they cannot explain. Gamma-ray astronomers find emission they cannot attribute. Radio astronomers find structures they cannot replicate anywhere else. Pulsar astronomers find absences they cannot account for. And when these communities compare notes, they find that their individual problems are not independent. They overlap, they interact, they feed uncertainty into each other. The galactic center is not producing one anomaly that a clever theorist might resolve with a single paper. It is producing a layered, interconnected web of anomalies that would require simultaneous breakthroughs in stellar dynamics, high-energy astrophysics, magnetohydrodynamics, and dark matter physics to fully resolve. This does not mean resolution is impossible. It means it is difficult in a way that is genuinely rare. The next generation of observatories is designed in part to address exactly this kind of layered problem. And understanding why these instruments matter requires understanding not just what they will observe, but how their specific technical capabilities map onto the specific anomalies at the galactic center. The Square Kilometre Array, currently under construction in South Africa and Australia, will bring radio sensitivity roughly 10 times greater than Meerkat. That factor of 10 is not merely incremental. In radio astronomy, sensitivity determines how faint a source you can detect. Many of the galactic center's mysteries involve objects that are either intrinsically faint or obscured by scattering. A 10-fold sensitivity increase means the SKA can detect pulsars that are 10 times fainter than the current detection threshold, which directly attacks the missing pulsar problem. If a hidden population of millisecond pulsars exists in the galactic center, obscured by the dense ionized medium, the SKA, operating at higher frequencies where scattering is reduced and with vastly greater collecting area, should be able to find them. If it searches and still finds nothing, the missing pulsar problem becomes a confirmed absence rather than an observational limitation, and the implications for dark matter physics become much harder to dismiss. The SKA will also resolve the internal structure of the radio filaments for the first time. Current Mir-KAT images show the filaments as thin lines. The SKA's angular resolution will reveal whether those lines have substructure, whether they contain internal braiding or helical patterns, whether the magnetic field within a single filament is uniform or varies across its cross-section. These details matter because different formation models predict different internal structures. A filament produced by a large-scale poloidal field should look different on the inside from a filament produced by a localized reconnection event. Resolving the interiors will finally allow astronomers to test the competing theories that have been debated since 1984. For radio transients, the SKA's survey speed will be transformative. Current surveys cover limited patches of sky with limited cadence. The SKA will be able to monitor the galactic center continuously over long periods, catching transient events that current telescopes miss because they occur between observations. If galactic center radio transients are as common as early detections suggest, the SKA should build a statistically meaningful sample within its first few years of operation. A large sample will reveal whether these sources share common properties that point to a single physical mechanism, or whether they are heterogate, requiring multiple explanations. Either outcome would be a breakthrough. The Cherenkov Telescope Array Observatory, or CTAO, operates on a completely different principle from space-based gamma-ray telescopes like Fermi. When a very high-energy gamma-ray photon strikes the upper atmosphere, it produces a cascade of secondary particles that travel faster than the speed of light in air, though not faster than the speed of light in vacuum. This faster-than-light in medium condition produces a faint flash of blue light called Cherenkov radiation, similar to the optical equivalent of a sonic boom. The CTAO will use arrays of large mirrors on the ground to detect these brief flashes, reconstructing the energy and direction of the original gamma ray from the pattern of Cherenkov light. This technique allows detection of gamma rays at energies far above what space-based telescopes can measure, reaching into the tera-electron-volt range, thousands of times more energetic than the GeV excess detected by Fermi. For the galactic center, the CTAO's angular resolution will be critical. Fermi's angular resolution at GeV energies is relatively poor, roughly half a degree, which means the telescope cannot clearly distinguish between a smooth, extended source and a collection of unresolved point sources blurred together. The GeV excess looks smooth in Fermi data, but that could be an artifact of limited resolution. The CTAO will achieve angular resolution roughly 10 times better at overlapping energies, potentially resolving individual sources within the excess, or confirming that the emission is genuinely diffuse. If the excess breaks apart into individual point sources at higher resolution, the pulsar explanation gains decisive support. If it remains smooth and diffuse, even at improved resolution, the dark matter interpretation becomes significantly more compelling. The next generation Event Horizon Telescope, an expansion of the existing EHT with additional stations, improved bandwidth, and new observing frequencies, aims to produce not just static images of Sagittarius A star, but movies. The current EHT captures snapshot averages of a source that changes on timescales of minutes. The next generation version, with more stations providing better coverage of the aperture plane and wider bandwidth providing more data per observation, will be able to reconstruct the time-variable structure of the accretion flow around the event horizon. These movies would show gas orbiting, spiraling inward, and potentially feeding a jet in real time. They would test theoretical models of black hole accretion in unprecedented detail, and could confirm or rule out the presence of the hidden jet suggested by the polarized light data. The jet question is not academic. If Sagittarius A star is currently launching even a weak jet, that jet carries energy and magnetic flux away from the black hole and into the surrounding environment. Understanding its power, direction, and variability would help constrain the total energy input from the black hole into the galactic center region, connecting the event horizon scale physics directly to the kilopascal scale bubble structures. A confirmed jet would also strengthen the case that past episodes of stronger jet activity inflated the Fermi and A Rosetta bubbles, linking the smallest and largest scale anomalies through a single physical mechanism. The gravity instrument at the Very Large Telescope Interferometer continues to track the orbits of S-cluster stars with micro-arcsecond precision. The 2026 apocenter passage of S2, the most precisely monitored star in the cluster, represents a specific opportunity to detect gravitational perturbations from the stellar population surrounding the black hole. At apocenter, S2 moves most slowly and spends the most time in a small region of its orbit, making it most sensitive to the cumulative gravitational tugs from nearby objects. If the perturbations are measured, they would provide the first direct constraint on the mass and number density of objects in the central parsec that are too faint to detect individually, opening a new observational window into the hidden population of compact remnants, stellar mass black holes, and other objects orbiting in the immediate vicinity of Sagittarius A star. And further in the future, Space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, could detect the gravitational wave signatures of compact objects spiraling into Sagittarius A star. These extreme mass ratio in spirals would provide exquisitely precise measurements of the black hole's mass and spin, map the space-time geometry near the event horizon, and test general relativity in the strong field regime with a precision impossible through electromagnetic observations alone. LISA would also be sensitive to the gravitational wave background produced by the broader population of compact binaries in the galactic center, providing an entirely new census of the region's contents that is independent of electromagnetic observations and unaffected by the dust, gas, and scattering that plague every other method. Each of these instruments addresses a specific layer of the anomaly stack. The SKA targets the magnetic structures, the missing pulsars, and the radio transients. The CTAO targets the gamma-ray excess and the dark matter question. The next generation EHT targets the black hole itself and its immediate accretion environment. Gravity targets the stellar dynamics and the hidden mass distribution. LISA targets the space-time geometry and the compact object population. No single instrument can resolve the full problem, but together they form a convergent observational program aimed at the most concentrated cluster of unresolved astrophysical questions in the galaxy. Whether this program will untangle the anomaly stack is genuinely uncertain. 3 outcomes are possible, and the honest answer is that nobody knows which one the data will favor. The first possibility is resolution. Improved observations reveal clean explanations for each individual puzzle. The gamma-ray excess turns out to be pulsars after all, once deeper radio surveys detect them hiding behind the scattering screen. The magnetic filaments yield to a single magneto-hydrodynamic model once their internal structures are resolved. The missing pulsars prove to be a scattering artifact that disappears at higher frequencies and greater sensitivity. The radio transients turn out to be an unusual but ultimately explainable class of magnetized stellar object. If so, the galactic center will transition from a region of overlapping mysteries to a region of overlapping solutions, and the sense of alarm will dissipate. This would be a triumph of observational perseverance, confirmation that the anomalies were never as deep as they seemed, just hard to disentangle from inside a complex environment. The second possibility is escalation, and this is the outcome that deserves the most serious attention because it is the one most consistent with the galactic center's track record. Every major observational advance directed at this region over the past 4 decades has produced more complexity, not less. The first infrared surveys revealed the S-cluster stars, which created the paradox of youth. The Fermi telescope revealed the GeV excess and the Fermi bubbles, neither of which was predicted. Meerkat revealed nearly 1,000 filaments where a few dozen had been known. The EHT revealed magnetic field structures suggesting a hidden jet. The Aero-Zetar telescope revealed even larger bubble structures enclosing the Fermi bubbles. At no point has a new instrument looked at the galactic center and found that the situation was simpler than previously thought. The pattern, consistently, has been the opposite. If this pattern holds, the next generation of observatories may sharpen each anomaly without resolving it. The SKA might search for pulsars and confirm definitively that they are absent, transforming the missing pulsar problem from a tentative puzzle into a hard observational fact that demands an explanation. The CTAO might map the GeV excess at higher resolution and find that it is neither cleanly smooth nor cleanly clumpy, but somewhere in between, fitting neither the dark matter model nor the pulsar model comfortably. The next generation, EHT, might confirm the hidden jet but find that its power is insufficient to explain the Fermi bubbles, requiring an additional energy source that has not been identified. Higher resolution radio observations might reveal a third population of filaments with yet another orientation, or discover that the filament spectral populations correlate with environmental variables in ways that no existing model predicts. Each new dataset would tighten the constraints without closing the case, leaving the anomaly stack intact but better defined, more precisely measured, and harder to explain away. This outcome, escalation without resolution, would be the most scientifically uncomfortable. It would mean that the galactic center is not just temporarily confusing but genuinely resistant to current theoretical frameworks. It would force researchers to confront the possibility that the models they use everywhere else in the galaxy are fundamentally incomplete when applied to conditions this extreme. And it would raise the stakes for the third possibility. The third possibility is unification. The overlapping anomalies at the galactic center may be connected. Not through the kind of direct causal link where one phenomenon produces another, but through a deeper underlying physics that manifests differently across different observational channels. If the dark matter concentration at the galactic center is responsible for both the gamma-ray excess and the missing pulsars, that would unify two anomalies under a single explanation while simultaneously providing the first indirect measurement of dark matter particle properties. If the magnetic field structure is maintained by energy input from the black hole's past active phases, and if that same activity inflated the Fermi and A Rho-Zetar bubbles, then the filaments and the bubbles become parts of a single magneto-hydrodynamic system, rather than separate phenomena. If the paradox of youth stars formed from a past accretion disk around Sagittarius A star, and if that disk was associated with the same active phase that produced the bubbles, then the stellar dynamics and the large-scale outflows share a common origin. These connections are speculative. None of them has been confirmed, but the mere possibility that the anomalies are related, rather than coincidentally overlapping, is what makes the galactic center so scientifically compelling. A region where multiple unresolved problems converge is either a place where bad luck has piled up, or a place where a single deeper explanation is waiting to be found. History favors the latter. When anomalies cluster in physics, they tend to be symptoms of something fundamental that existing frameworks have missed. The ultraviolet catastrophe and the photoelectric effect seemed like separate problems until quantum mechanics unified them. The perihelion precession of Mercury and the bending of starlight seemed like separate puzzles until general relativity explained both. The galactic center may be presenting astrophysics with a similar cluster of symptoms, each one individually manageable but collectively pointing toward a regime of physics that current models have not yet fully captured. This does not mean that the galactic center will yield a single revolutionary insight. Science does not always work that way. Sometimes, overlapping anomalies resolve into overlapping mundane explanations, each one unrelated to the others. The history of astronomy is full of false convergences, cases where mysterious signals turned out to have prosaic causes that were difficult to identify, not because the physics was new, but because the observations were hard. The galactic center could belong to that category. The gamma-ray excess could be pulsars. The missing pulsars could be scattering. The filaments could be a magneto-hydrodynamic curiosity specific to high-density environments. The radio transients could be a new but ultimately ordinary class of variable star. If so, the alarm was premature, and the galactic center will take its place as a complicated but ultimately comprehensible astrophysical environment. But even in that scenario, something important has been revealed. The center of our own galaxy, the nearest galactic nucleus, the one laboratory where we can study extreme astrophysical conditions in detail, is harder to understand than we expected. Every assumption that makes astrophysics tractable in ordinary environments, that star formation follows standard pathways, that pulsar populations scale with stellar populations, that magnetic fields are a minor perturbation on gas dynamics, that gamma-ray backgrounds can be cleanly subtracted, turns out to carry hidden dependencies on conditions being moderate. The galactic center is where those conditions stop being moderate. It is where every comfortable assumption gets tested at once, and none of them are surviving the test cleanly. And perhaps that is the deepest lesson the galactic center has to offer. Regardless of how any individual anomaly eventually resolves, we built our understanding of the universe from the quiet neighborhoods. We studied star formation in calm molecular clouds. We measured magnetic fields in the peaceful interstellar medium. We counted pulsars in the suburban outskirts of the galaxy. We developed gamma-ray models calibrated to average galactic conditions. Then, we pointed those models at the single most extreme environment within reach and discovered that they buckle under the pressure. The galactic center did not break physics. It revealed where physics was never tested. It showed us the boundaries of frameworks we assumed were universal, and it did so not through one dramatic failure, but through a slow, accumulating series of anomalies that refuse to go away. That is what the title of this story ultimately means. Scientists are not panicking because they found one strange thing. They are unsettled because the center of the Milky Way keeps producing different kinds of strange things, all at once, all in the same place, and none of them quite resolving despite years of dedicated study. The galactic center is not a single mystery. It is a pressure point where gravity, radiation, magnetism, stellar dynamics, and potentially dark matter all become extreme enough to push the boundaries of current understanding in overlapping ways. The anomalies do not cancel each other out. They reinforce each other, each one making the others harder to dismiss, each one adding a layer of complexity that the next must account for. The Milky Way looks peaceful tonight. That soft band of light will stretch across the sky the same way it did when the first humans looked up and wondered what it was. But behind the glow, at the exact center, in a region you could never see with your eyes no matter how dark the sky, something is piling up. Stars in impossible orbits, radiation without a confirmed source, magnetic structures found nowhere else, signals that match nothing in our catalogues, pulsars that should be there but are not, bubbles of energy erupting from the core and reaching halfway across the galaxy. Not one discovery, not one headline, a whole environment of overlapping unknowns concentrated in the heart of the galaxy we call home. And every new instrument we build to look at it finds another layer we did not expect. The center of the Milky Way is not just one mystery. It is the place where several of the most important unresolved problems in astrophysics have chosen to converge. And that convergence, that relentless accumulation of anomalies in a single location, is what is quietly keeping scientists awake. Not because they know the answer is frightening, because they do not yet know the answer at all.